Griffiths, Unum section 1.2.2 and 1.2.3, the beginning of derivatives or differential calculus with vectors. So suppose I have some function, let's call that function t, and I want to know how much t changes as I change a variable, right? I think we would describe that change as some dt. All right. And now I want to know what that total change in t is as I change some variable. Let's call it, in this case, x. All right. I can go ahead and evaluate my function at different points, and I can see the total change in that function as just the infinitesimal changes along infinitesimal changes in my independent variable, right? So I can go ahead and evaluate that change dx, which is just connecting these 2 points, and that is dt dx, right? dt dx. I can go ahead and evaluate the next infinitesimal change in x, evaluate a new slope, dt dx, and evaluate another new slope, dt dx. So my total change in my function is just going to be adding up the infinitesimal changes that are being made as I change my independent variable. Okay. Another way to write that without the summation that you might expect here is that my total change is just the infinitesimal change in my function as I change my variable, dtx, that's the slope right there, times how big that change is. We can then apply this to multivariable objects, and in doing so, we're going to end up defining what is called a gradient. Okay, so let's say I have another variable or another function called t, and t is now a function of x, y, and z. So it's no longer a one-dimensional function. If I want to know what the total change in my function is, I need to add up the components, the changes in all of the different directions. This is a theorem of partial derivatives that you might have seen in the past. So I can take the partial of my function with respect to x and multiply it by how much I've changed in x. I can then do the partial of my function with respect to y and how much it changes in y, and the partial of my function with respect to z and how it changes in z. All right, just like I did in the 1D case. Now we have partial derivatives because there's multiple variables, but the same kind of idea exists. All right, so now I have some dependence on x, some dependence on y, and some dependence on z. Now, it may not be obvious that you can do this, but this is looking like the output of a dot product, right? If I were to rearrange this equation, I could go ahead and say that these partial derivatives with respect to t, dx in the x hat, plus dt, dy in the y hat, plus dt, dz in the z hat, that can be one vector of my dot product, and another vector would be dx in the x hat, dy in the y hat, plus dz in the z hat. Pause the video right now to convince yourself that if you take the dot product of this line, you end up with this original expression above. Okay, so now that we've described the total change in my function as a dot product of two different vectors, let's go ahead and give those two different vectors names. This first vector we are going to call the gradient of my function, and it is dotted with the second vector, which we're going to call the infinitesimal displacement vector, dl. So I have some small change in some arbitrary set of directions. That is my infinitesimal displacement vector. And this set of derivatives is the gradient of my function. Okay, so let's get an idea what this gradient really means. Okay, so I have this function t. T is a function of x, y, z, so it exists over all space. And I want to know what the total change in my function t is. Okay, now I can go ahead and rewrite dt above just with our formalism of taking the magnitude of my gradient times the magnitude of my displacement times the cosine of the angle between them. Okay, so let's just draw that just for fun. This is my gradient vector. This is my infinitesimal displacement vector, and this is the angle between them. So if I keep my displacement vector constant, what direction should my gradient vector point so that I maximize dt? Well, the only way to change the value of dt is by changing the relative orientation of my gradient vector and my infinitesimal displacement vector. Okay, what angle of theta maximizes cosine of theta? That's theta of 0. So my gradient vector that maximizes my change in my function is pointed along dl, which means that my gradient points in the direction of biggest change in t, or if you want to talk about it in terms of slopes, this is pointing in the steepest slope. All right, let's calculate a gradient together then. Okay, so this is example 1.3. I have a function r, which is the square root of x squared plus y squared plus z squared. So it's the radius of a sphere. And I want to know what is the gradient of this function. Okay, so let's just write that down. The gradient is then the partial of r with respect to x in the x hat direction, the partial of r with respect to y in the y hat direction, and the partial of r with respect to z in the z hat direction. All right, all of these, because of how consistent this looks, all of those derivatives are going to look the same. So let's go ahead and do one of them together, and I'll extend the solution to all of them. So I can write this as r is equal to x squared plus y squared plus z squared to the 1/2, and then this first term, dr dx, I get a 1/2. I get this whole thing again, x squared plus y squared plus z squared, but now it's to the minus 1/2, and then the derivative inside with respect to x becomes 2x, or call it x hat. Okay, the second term looks very similar. 1/2 x squared plus y squared plus z squared to the minus 1/2 2y, y hat, plus 1/2 x squared plus y squared plus z squared to the minus 1/2 2z, and z hat. All the 1/2s and the 2's cancel. All of the denominators are the same. X squared plus y squared plus z squared square root. And we're left with x hat plus y hat plus z hat. All right. We know what our position vector looks like from previous videos. This is just the position vector. And this is the magnitude of that position vector. So the gradient of my position vector, the gradient of the magnitude of my position vector becomes r hat. All right, so this gradient that we've looked at has derivatives, has a function embedded into it, and it has unit vectors that make it a vector. All right, so this gradient of my function can then be rewritten, right? It can be rewritten as some product of x hat d dx, where this is the derivative with respect to x, plus y hat d dy, plus z hat d dz of my vector, or of my function rather. All right. Previously, we've just been writing the t's inside of the derivatives, but that's the same function, so we don't have to write it like that. This bit right here has a special name. That is the del operator. All right, del operator acting on the function, del operator acting on the function. So my del operator is x hat d dx plus y hat d dy plus z hat d dz. This operator is a vector, and it acts on something. In the case of the gradient, it acted on some scalar function t. But this del operator acts like a vector in the traditional sense. I can go ahead and act that on a scalar function t, like I did the gradient. I can take the dot product of some vector, and I can take the cross product between my del operator and some vector. I'll go into more about these two on the next video.